Listen to the silence of the hangar. This machine rests in the darkness. It is cold. It is silent. It is waiting. This is not a mere assembly of metal. It is a monument of titanium. It is a titan of carbon fiber. Look into the massive dark intake. Look closely at the sculpted fan blades. 16 carbon fiber blades. Only 16. Older engines required dozens of blades. This engine needs only 16. Each blade is a masterwork of aerodynamics. Each blade features steel trailing edges. They sweep backward with absolute purpose. Measure the diameter of this circle. It spans 134 inches across. 134 inches. That is 11.2 feet of open space. That is 3.4 meters wide. Think about that scale. That opening is wider than an entire cabin of a Boeing 737. An entire passenger jet line fits inside this engine mouth. A single person stands dwarfed beside it. A tall human cannot reach the top edge. It is gigantic. It is terrifying. Now look at the financial numbers. Look at the price tag stamped on this hardware. One single engine. Just one. It carries a list price of $45 million. Read that price again. $45 million for one power plant. To hang two of these giants under a wing cost nearly $90 million. $90 million just to generate thrust. That does not include the airframe. That does not include the interior seats. That does not include cockpit avionics. $90 million for propulsion alone. Compare that to luxury aviation. $90 million buys several brand new private jets. It buys a fleet of business aircraft. Yet airlines pay it for one pair of engines. Look at the historic engines before it. Look at its famous predecessor, the legendary GE90-115B engine. The GE90 powered the famous Boeing 777-300ER. It was long considered the king of wide-body skies. The GE90 listed at $30 million. $30 million was considered astronomical back then. Look across the ocean at European competition. Look at the Rolls-Royce Trent XWB. It powers the modern Airbus A350. The Trent XWB lists for roughly $25 million. The GE9X leaves them all in the dust. It shatters every previous financial barrier. It obliterates historical cost benchmarks. Why? Why does this single machine cost so much money? The answer starts decades in the past. It begins inside high-tech research centers. Engineers did not build this overnight. This engine was 30 years in the making. General Electric spent 3 decades refining composite technology. 3 decades of continuous research. They created the first generation of composite blades for the GE90. They tested second-generation blades on the GE9X engine. They developed third-generation blades for the CFM LEAP. Now they reached the 4th generation. The GE9X represents 4th-generation composite technology. Every generational leap required massive capital. Every single design iteration cost billions. Engineers destroyed prototype engines on test stands. They fired ice blocks into rotating fan blades. They dumped tons of water into burning combustion chambers. They pushed metal parts past their physical limits. Failure was mandatory during research. Every failure taught them lessons. Every lesson required more funding. Overall engine development surpassed $10 billion. $10 billion before selling a single production engine. Look at the infrastructure costs. Building the engine required new factories. General Electric spent $4.3 billion on domestic manufacturing plants. $4.3 billion inside the United States alone. They spent another $1.1 billion on overseas construction. They spent $600 million on complex factory tooling. Specialized robots were designed to weave carbon fibers. Custom furnaces were built to fire advanced ceramics. $10 billion in upfront corporate risk. $10 billion of initial investment capital. Now, the global aviation market pays that bill. Step closer to the machine itself. Look beyond the giant fan blades. Look into the heart of the engine core. Inside this casing live 35,370 individual parts. 35,000 individual components. Every single part must operate with absolute perfection. There is no room for structural error. There is no tolerance for mechanical failure. Consider the physical pressures deep inside. The overall pressure ratio reaches 60:1. 60:1. That is the highest pressure ratio in commercial history. Air enters the intake at atmospheric pressure. The compressor squeezes that air down 60 times smaller. The air becomes extremely dense. The air becomes intensely hot. It flows directly into the combustion chamber. Fuel sprays into the compressed airstream. The mixture ignites with immense energy. Look at the internal temperatures. Temperatures inside exceed 2,000 degrees Fahrenheit. That heat melts conventional aerospace metals. Standard steel softens like butter in that heat. High-grade titanium fails under those conditions. Engineers needed something entirely new. They turned to space-age chemistry. They forged ceramic matrix composites. Ceramic Matrix Composites. Engineers call them CMCs. Over 100 components are built from CMCs. CMCs embed ceramic fibers inside ceramic matrices. The material is extremely lightweight. The material is tough as forged steel. Most importantly, it survives extreme heat. It withstands temperatures that melt nickel alloys. It does not require heavy cooling air channels. Less cooling air means greater engine efficiency. Greater efficiency saves massive amounts of jet fuel. The GE9X burns 5% less fuel than competing engines. It cuts fuel burn by 10% compared to the GE90. A 10% fuel reduction saves airlines millions every year. Airlines pay massive upfront prices and to buy that fuel-saving technology. Here lies the economic secret, the real reason for the price tag: monopoly. In past decades, airlines chose their engines. A buyer of an older Boeing 777 had choices. They could select Pratt & Whitney. They could select Rolls-Royce. They could select General Electric. Competition kept prices grounded. Not anymore. Boeing built the 777X around one single power plant. The GE9X holds a total monopoly on the 777X. Airlines are captive customers. If an airline buys a 777X, it must buy from General Electric. There is no alternative. Look at Emirates, the world's largest 777X customer. They committed to hundreds of aircraft. In 2013, their initial commitment translated to roughly $53.3 million per engine package. $16 billion just for engines. Then came the maintenance contract, another $16 billion for a 12-year agreement. Look at Singapore Airlines. They paid $2.9 billion for 22 GE9X engines with service agreements. That averages $127 million per engine over its service life. The engine purchase is just the down payment. The maintenance contract is where true fortunes shift hands. Raw power requires absolute perfection. During testing, the GE9X smashed world records. It generated 134,300 pounds of thrust. That makes it the most powerful commercial jet engine ever created by human hands. Yet, push extreme limits, and nature fights back. The engine faced steep challenges during certification. During flight testing, inspectors found a flaw. A crack appeared in a mid-seal component inside the turbine core. The mid-seal separates critical high and low pressure turbine stages. Immense thermal stress produced concentrated friction points. A simple quick-fix patch was impossible. General Electric had to pause and engineer a complete redesign of the hardware. Every delay adds millions to the total bill. Every redesign pushes certification timelines further back. To earn certification, this engine must endure torture. Over 30,000 test cycles, 9,000 endurance cycles, 1,600 dust ingestion trials. Engines blasting fine sand directly into hot turbine cores, proving durability under hostile skies. The GE9X is an engineering marvel. It is massive, it is efficient, it is ruthlessly expensive. 30 years of development, $10 billion in infrastructure, monopoly pricing power, exotic aerospace materials. $45 million buys more than an engine. It buys the outer envelope of human aviation.